Traditionally, the small explorers are launched from a small rocket called a Pegasus. And it flies out of the upper atmosphere as its first stage, and then it has a more conventional second and third stage. The main objective of GALEX is to measure the star formation rate in galaxies. And it turns out that to measure the star formation rate, we need to look at only the very hot stars that have a short lifetime. Looking at a galaxy with GALEX is like taking a picture of a crowd of people and having everybody over the age of 5 suddenly disappear from the picture. You're left with just the very young stars that tell you how active star formation is in a galaxy.
One of the best moments in this project for me was early on, maybe a few weeks after launch, when we had the instrument turned on and saw our first picture of the ultraviolet sky from the Galaxy Evolution Explorer. And it was filled with galaxies. And it was just a 2-minute picture, just a short amount of time. And yet we already saw that the universe was filled with galaxies luminous in the ultraviolet. And here we were looking at 1/40,000th of the sky. It was an amazing, thrilling moment. It's exactly what I had always hoped and dreamed for, but you never quite believe you're going to get there, and there we were.
The Spitzer Space Telescope shows us the universe in an entirely new way of looking at it, infrared light. Infrared light shows you some very specific and interesting astronomical things, like young stars or black holes in the very hearts of the most active galaxies are shrouded by dust. And that makes them completely invisible to the sort of light that our eyes see, visible light. But infrared light gives us a view inside these mysterious areas, and we're getting the clearest views we have of that for the first time.
You're sitting somewhere in your house on a weekend and you realize while you're sitting there, Spitzer is very far away, pointing at sources, taking fabulous images. Twice a day we're sending these things down all across the globe through the Deep Space Network. It truly is remarkable. We're looking at things that happened so long ago and are happening so far away.
I think we're going to get a much, much better understanding of the formation and prevalence and evolution of planetary systems within our galaxy. And I think we've already learned some things about the dust component of the planetary systems that are kind of going to change our view of the processes which might have influenced the early Earth. Spitzer is a technological precursor to a lot of future NASA missions. So we kind of crossed a lot of technical divides, and people will never look back to the old way of doing things.
Remember now, this whole MER project was predicated on the idea that we'd be able to use Mars Pathfinder, not just the concept, but the design, the detailed design, because that's where all the work is. Suddenly, the idea of using Pathfinder design started to crumble. The concepts are old, or at least the ideas of the design are the same, but you don't fly ideas, you fly hardware.
There was no strategic plan after that. It was just, take this hill, take the next hill, take the next hill.
You got to believe it's going to happen, or it's just like, why am I doing this? You just have to sort of feed on that confidence. So it's a group psychosis, I guess, is probably the best way to describe it. So
3, 2, 1, start and liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
Load relief kick rate is in, vehicles responding. Vehicles recovering very nicely from the liftoff transients.
Program response is good. 3, 2, start, 0, and liftoff of the Delta rocket with Opportunity, a chance to explore and unlock the secrets of our neighboring planet.
The transients at liftoff. Engine position looks good.
We had gone through a rather stressful week leading up to landing. One was that we had had a global dust storm. What should we do about modeling this? How do we know that our system's going to work? But what's the other thing? Well, much to our surprise, after months and months and months of successful round-the-clock testing, we finally find that there's some failures that are occurring. We had 3 failures. We said, well, is it fluke? What's going on? What we've discovered is that the software is trying to turn on timers that count down to firing pyrotechnic events that, say, opens up the parachute or inflates the airbag, fires the rocket, or cuts a cable. We're finding that the software wasn't getting around to doing it. It tried, but the hardware didn't work. And there was a problem between the hardware and software that we did not know about until just 2 days before landing, in which case we'll have a failure, guaranteed failure. We're pretty nervous about this.
Show us your uncertainty, show us your estimate of your unknown unknowns, but don't...
Well, the first thing that comes to our minds was that we can manually do it by sending commands from Earth to bypass the limitations that were present during landing to make those pyrotechnic devices go.
It was one of those, there's a probability it's not going to do it. Probability is probably very low, but we have to counteract it by sending this real-time command, but we really haven't tested that approach, and so how do you want to play?
Flight nav.
Go nav.
The Doppler signature indicates cruise stage separation has occurred.
Copy that.
All systems are go for entry, descent, and landing. We are currently 6 minutes from landing at the Gusev crater in the southern hemisphere of Mars.
MGS is green and Mach is ready to record.
Atmosphere entry.
5, 4, 3, 2, 1, mark.
The vehicle has now hit the top of the Martian atmosphere, moving at a speed of 12,192 miles per hour. Downrange distance to the landing site is 437 miles.
You're going through an event like that, where everything that you've worked for so many years is on the line. We had no control.
Current altitude 45,000 feet. Current velocity 1,356 miles per hour. Expected parachute deploy in 5 seconds. 4, 3, 2, 1, mark. We are awaiting confirmation the parachute has deployed. Parachute lift detected. Lander separation event detected. Spacecraft reporting lander is separated. We expect that radar will lock on the ground in approximately 5 seconds from now. Current altitude 8,000 feet. Moving at a speed of 173 miles per hour. We are near our terminal velocity. Spacecraft reporting that the radar is in lock and we have a good solution on the ground. Expected retro rocket ignition on my mark. Awaiting confirmation from the spacecraft that retro rocket ignition has occurred. At this point in time, we should be on the ground. Now 6 minutes, 37 seconds from atmospheric entry. Still awaiting signal that we are on the ground. Stand by.
In fact, it took me a while to even believe the signal was really there when Polly was saying, Rob, there's a signal. I go, where? Show me. I don't see it yet.
I think my main reaction was relief. I think is probably the main thing. It's like, oh, we made it.
The electronic tone sent from the rover indicates that the rover has landed base pedal down, which means right side up.